Hello students, welcome back. Let us resume our discussion in section 1. Previously we completed up to 1.3, so let's resume from 1.4, the multiplicative property. What do you mean by an arithmetic function is multiplicative? It means this. The arithmetic function preserves the multiplication for any pair of positive integers that are relatively prime. That's what it means. Now, can you think of an example? In other words, examples of arithmetic functions that are multiplicative or that are not multiplicative. Well, in 1.2, we went through a number of important examples, tau and sigma, and then their generalization, sigma k, and then the most important of the bunch, phi, and finally, a little bit of a sideshow, but nu p. What do you think? Well, it turns out all these are multiplicative. The last one here is not. So how do you prove these claims? Well, what do you think? To prove or to disprove? Which do you think is easier? Well, in my opinion, to disprove is a bit easier because all I need is just one counterexample. So how about a claim that p-adic valuation function is multiplicative and to disprove it, or claim that is not multiplicative and then prove through an example, whatever you may want to say. Let's do that first. Let's prove that p-adic valuation function is not multiplicative. For that, we need just one example, so think of an example. Stop the playback and think of an example. Did you get it? Well, there can be a lot. There are infinitely many examples, of course, but I just selected one. Nu3 of 90 is Nu3 of 9 times Nu3 of 10. Turns out no. Nu3 of 90, it follows from the prime factorization. We are looking for the top power of 3, as I highlighted in green, so that's 2. And same for Nu3 of 9. But Nu3 of 10 is 0. And 2 is not equal to 2 times 0. So yeah, that completes the proof. Or that completes the disproof, whatever you may want to call. By the way, it turns out that p-adic valuation function is additive, not multiplicative, but additive. Here, please note that 2 is not 2 times 0, but 2 plus 0. Indeed, here's a definition of the additiveness. Additivity, rather. So replace this multiplication here into addition. That's the definition of the additivity. By the way, in this particular case for p-adic valuation, we don't even need this. This conclusion is true no matter what. In this case, we say the arithmetic function is completely additive. Turns out p-adic valuation is completely additive. The proof is pretty simple. And as we did in the previous problem here in this example, let's go back to the prime factorization. Thanks to the fundamental theorem, we can rewrite m and n as p to the whatever power times other primes, and also p to the whatever power times other primes, appropriate for m and n. And then if we multiply them together, what do you get? P to the sum of the powers times other prime factors. Conclusion? We have the additivity, and the additivity does not depend upon this GCD condition. It's always true. So we say that the p-adic valuation function is completely additive. But then again, that is not something that we are going to focus upon too much. I mean, it was a good exercise, and then, yeah, it's a good exercise and it's a good use of prime factorization. So I may pick up and write something like that to the exam or things like that. Yeah, that's true, but still, far more important topic is the multiplicative property, not the additive property. So do not completely forget about this p-adic valuation function, but remember the real focus is the multiplicative property, not the additive property. And let's resume discussing the multiplicative property with this big theorem. Let small f and capital F be arithmetic functions related like this. Capital F of n is the sum of all small f of d, where d is a positive divisor of n. Here I used only d dividing n, the divisor, but the positiveness goes without saying because all those arithmetic functions are defined for positive integers. And as for this summation for all positive divisors, please remember the summation because it appears in all kind of different places whenever we consider arithmetic functions. And one of the biggest reasons that is the case is right here, thanks to this theorem. There are other reasons too, but this is probably one of the biggest reasons. Maybe not the biggest, or possibly, well, I don't know. It's certainly one of the biggest reasons. So this is important. Pay attention here. Okay, if small f is multiplicative, then so is big F. And basically, this is what we want to prove. The definition of the multiplicative property. Okay, let's see, to save some space, let me copy and paste. Okay, there you go. All right, that's what you want to prove. But before that, let's set up and prove a lemma. A lemma that is not directly related to arithmetic functions or of any kind, but it's going to be useful for this. Assume m and n are relatively prime. We claim that every divisor d of m times n can be uniquely decomposed into divisor of m, which we call a, and the divisor of n, which we call b, that are relatively prime. If you rewrite symbolically, it goes like this. M and n are relatively prime, okay? And then every divisor of m and n, so d divides m and n, then d can be decomposed into a times b, actually uniquely decomposed to a times b, and then divisor of m and divisor of n. So a divisor of m and b divides n. And finally, a and b are relatively prime. So we can classify the conclusion like this: blue, purple, and green. And then as a side show, we have the uniqueness as well. So let's prove this lemma first, and then let us utilize this lemma to prove the theorem. How do you prove this? Well, this lemma has nothing to do with arithmetic functions, so I could have left it as an exercise, but let's go ahead and do that. From the fundamental theorem, m and n can be decomposed to prime factorization like this. P to the n powers, q to the n powers like those, and then p's and q's are all different. Because m and n are relatively prime, they do not share any prime factor. Alright, so what did you just use? We used the fact m and n are relatively prime. And then if we just multiply those, then we have these. And yeah, p's and q's are all different, remember that. Okay, and then let's use the divisibility. D divides m by m times n, let's use that. So d can be decomposed into prime factorization as p to the sum powers and q to the sum powers, where all those powers of p should be less than the powers of p's for m, so that, yeah, d divides m, so, and same goes for q's. That's because d divides m and n. Make sense? From the fundamental theorem again. So this prime factorization must divide that prime factorization. So each prime factor has to have lower power, possibly even 0. Now A and B are pretty clear. I'm going to define this one as A and that one as B. Consequently, I'm going to get that equals to A times B. And thus we have this decomposition. A is defined as this prime factorization, B is defined as that prime factorization, then D is A times B, as you saw here, and A divides M and B divides N because the powers of P for A is less than that for M, and also same for B versus N. And the prime factors are all different, so they're all relatively prime. So you see in this color coding, you can see all these conclusions that we need and what part is causing what conclusion through all these color coding. And as for the uniqueness comes from the fundamental theorem. The fundamental theorem says the prime factorization not only exists, but exists uniquely. So uniqueness comes from the fundamental theorem. Okay, so much for the lemma, and here's the proof. Okay, now let's talk about how to utilize this lemma. What we want to prove is this. So we want to start from the left-hand side and manipulate. We want to get to the right-hand side. And at some point, we have to use the fact M and N are relatively prime. And of course, we used it to get this lemma. Okay, all right. Here is the computation, the first line of the computation. Capital F of M times N is, by definition, the summation of F of D, which is directly the definition. And then let's utilize this lemma. D is A times B. Is that clear? It's highlighted in blue. And then D divides M times N. Yeah, all right. Thanks to that, A divides M and B divides N. I should have highlighted all those. There you go, in purple. So we just used blue and purple. And then remember, A and B are relatively prime. See, relatively prime. And then small f is multiplicative. F is multiplicative. So this small f of A times B can be decomposed further into this. F of A times F of B, like this. Okay, from this point on, it's easy. A divides M and B divides N. Let's decompose, rewrite the summation into B divides N first, add them all up, and then A divides M later. Inside has to be done first, you see, and then factor F of A out, and all of a sudden we get what we want. A divides M, F of A, B divides N, F of B, which gives rise to capital F of M times capital F of N. So the lemma applies to this colored part. After that, it's just a general property of the summation. Just associativity, and then commutativity and distributivity of real number arithmetic. That completes the proof of this theorem. And then from here, you can immediately prove that tau and sigma are additive, and so is sigma k of n, and that detail is left to the students. You see, you have all those summation expression. So you can apply this theorem. All right, that completes section 1.